of this lecture. In my previous video, I had defined what is the principal axis theorem. Today, at first as a review, I will indicate this statement of this principal axis theorem. Then, I will say when two quadratic forms are equivalent. In my previous video, I have seen what is the index signature of quadratic form. Today, I will say when two quadratic forms are equivalent, then index, signature, inertia of these quadratic form are always equal. At first, just as a review, just recall the principal axis theorem. AB real symmetric matrix with eigenvalue lambda 1, lambda 2 up to lambda n. And if we form the orthogonal matrix P, then substitute x equal to Py, then the quadratic form x transpose Ax by the principal axis, this is reduces lambda 1 y1 square up to lambda n yn square, and the equation would be such type. Consider qx equal to 13x1 square plus 10x1 x2 plus 13x2 square equal to 72. Obviously, this quadratic form is look like such type where A is symmetric matrix. Then, by principal axis theorem, we can tell this is reduces new quadratic form 8y square plus 18y2 square equal to 72, where 8 and 18 be the eigenvalue of this matrix. Now find the eigenvector with respect to the eigenvalue lambda equal to 8. The eigenvector is 1 over square root times 1, the column vector 1 minus 1, and with respect to eigenvector value lambda equal to 18, the eigenvector is 1 over square root times the column vector 1 1. And here new qx would be such type x1 comma x2. First eigenvector with respect to eigenvalue 8, 1 over square root of 2 minus 1 over square root of 2. And here 1 over square root of 2, 1 over square root of 2. Here, if we consider this matrix is Q with eigenvector, then this would be the Q transpose matrix. Just notice, this is the transpose of this matrix. Here also, this is the eigenvector. Here this is the eigenvector with respect to 8 and this is the eigenvector with respect to 18. x1 comma x2. And here new transformation is obviously y transpose dy, where y equal to y1 comma y2 coordinate along the coordinate, which is equal to this term. Therefore, the new transformation, this quadratic form transform this quadratic form, and this is actually ellipse. And actual picture is this is x1 x2, and consider this eigenvector y1 and this eigenvector y2, and with respect to these two eigenvector, this is represent as a ellipse. I hope my all viewers have understood this type of concept. Actually, I have defined in my previous video elaborately. So at first I will highly recommend you, if you don't see my previous video, then at first see my previous video. We all of us know two symmetric matrices A and B are congruent if there exists an invertible matrix P such that A equal to P transpose BP. This is the definition of congruent. We all of us know this definition. So, actual principal axis theorem, this associated matrix and this matrix D is congruent to each other. So, for this example, for this quadratic form, here the associated matrix is this, and I have got new matrix whose eigenvalue, whose diagonal entry is only eigenvalue and other part is 0. So, obviously, these two matrices are congruent. What is the congruent of quadratic form? Two quadratic form x transpose ax and y transpose by over the field F are said to be congruent or equivalent over the field F if their associated matrices A and B are congruent over the field F. That means two quadratic form are congruent if associated matrices are congruent. And since congruent of matrices is equivalent relation, so congruence always quadratic form is an equivalent relation. Now I will define one new term, inertia. A real symmetric matrix A is defined to be triplet which is indicated as rho nu xi, in which rho nu xi are the respective number of positive, negative and zero eigenvalue counting algebraic multiplicity. This is the concept of inertia. For example, consider AB 4 cross 4 matrix whose eigenvalue is 2, 2, minus 1, 0. Then inertia of A, which is denoted as rho sigma xi, which rho means actually number of positive eigenvalue, this is 2, sigma means number of negative eigenvalue, this is 1, and xi means number of zero eigenvalue, this is 0. Similarly, if we consider the eigenvalue 2, 1, minus 1, 0, then number of positive eigenvalue is 2, number of negative eigenvalue is 1 and number of zero eigenvalue is 0. I hope my all viewers have understood the concept of inertia. Now I will tell you how the inertia of the matrix A related congruence of quadratic form. Now I will say Sylvester's law of inertia. What is the Sylvester's law of inertia? Sylvester's law of inertia states that A is congruent to B if A and B have same inertia. This is the Sylvester's law of inertia. Same inertia means number of positive, negative and zero eigenvalue are same. And we all of us know, in previous video I have discussed number of positive terms in a canonical form of a quadratic form is called index of quadratic form. And what is signature? The number of positive term minus the number of negative term in a canonical form is called the signature. That means if number of positive term is P and number of negative term is N, then S equal to number of positive term minus number of negative term, P minus N. Second concept, if R be the rank of quadratic form and P be the index and S be the signature, we all of us know rank means number of non-zero entries in the normal form, then S equal to 2P minus R. And two symmetric matrices A and B are congruent if and only if the canonical from A and B have the same rank, index and signature, then we can tell two matrices A and B are congruent to each other if they have same rank, same index and signature. This is the concept. How I will check two canonical from are congruent or not. An alternative statement of congruent is two symmetric matrices A and B are congruent if and only if their diagonal representation have the same rank, index and signature. And this is the easy method to find when two quadratic form are equivalent to each other. That means at first we have to find the diagonal representation of the matrix A and B. Then we have to find, is this diagonal representation have same rank, index and signature? If they have, then they two are congruent to each other. Then determine which of the following matrices are congruent to each other. This question I will see by Sylvester's law. Notice in the first matrix A, the eigenvalue are 4 plus minus square root of 6. Then number of positive eigenvalue, signature and zero eigenvalue is 2, 1, 0. And for the matrix B, consider the eigenvalue. Find the eigenvalue. This eigenvalue would be 0, 5 plus minus square root of 30, 33 over 2. And here rho sigma chi means number of eigenvalue, positive eigenvalue and zero eigenvalue would be 1, 1, 1. And the eigenvalue of C is 1, 1 plus minus square root of 5. Here rho sigma chi means number of inertia, number of positive eigenvalue is 2, number of negative eigenvalue is 1 and zero eigenvalue is 0. Notice here the inertia is same, rho sigma chi is same. So by Sylvester's law we can tell A is congruent to C. I hope my all viewers have understood how Sylvester's law we can tell one matrix, two matrix or three matrix be congruent to each other. Now I will see one question which had come CSR net exam. The question is, consider three quadratic from q1 x comma y equal to xy, q2 x comma y equal to x square plus 2xy plus y square and q3 x comma y equal to x square plus 3xy plus y square. Now choose the correct statement from the below. Option 1, q1 and q2 are equivalent. Option 2, q1 and q3 are equivalent. Option 3, q2 and q3 are equivalent. And option 4, none of this. For this, I will just use the Sylvester's criteria to find is this quadratic form is equivalent or not. For this, consider q1 xy equal to xy. And by this quadratic form, we can associate one matrix 0, half, half, 0. And notice the eigenvalue of this matrix is plus minus half. Now I will find the inertia rho sigma chi, where rho is number of positive eigenvalue, sigma is number of negative eigenvalue and chi is number of zero eigenvalue. And this is, notice here one positive eigenvalue and one negative eigenvalue. So this is 1, 1 and there exists no zero eigenvalue. So this is 0. And for Q2, here the quadratic form is this. By this quadratic form, we can generate this matrix and here the eigenvalue is 0 and 2. Therefore, the number of inertia which is denoted as rho sigma chi, this is here one positive eigenvalue and one zero eigenvalue. Therefore, number of inertia 1, 0, 1. Because there exists sigma means there exists no negative eigenvalue. and Q3, this xy equal to this quadratic form, and this quadratic form generate this matrix. By this matrix, we can evaluate the eigenvalue, and here the eigenvalue would be such type, that means here one positive eigenvalue and one negative eigenvalue. So inertia, which is denoted as rho sigma xi, which is actually 1 1 0, that means number of positive eigenvalue is 1, number of negative eigenvalue is 1, number there is no zero eigenvalue. So since notice here for Q1 the inertia and for Q3 the inertia are same, that means number of positive, negative and zero eigenvalue are same, but for Q2 the inertia is different. So option 1 is a right option. Sorry, option 1 is a wrong option. Here indicate Q1 and Q2 are equivalent. This is wrong option. Only option 2 is a right option, because 2 indicate Q1 and Q3 are equivalent, and option 3 are wrong option. Q2 and Q3 are equivalent. This is wrong option. Also option 4 indicate none of this. This is also wrong option. Only option 2 is a right option. Q1 and Q3 are equivalent. I hope my all viewers have understood this concept. How by finding eigenvalue and by the concept of inertia we can tell quadratic form are equivalent. Okay? Well, today I will stop here. In my next video I will continue this type of concept again. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe.